Okay. So, okay. So today in this recording, we will finally start talking about forces on a fluid element. And the forces, the reason it's more complicated than a normal point particle motion that we study in earlier days, in earlier classes, is because now an element of the fluid has also surface forces, viscous forces, surface and shear forces, which has pure deformation. Now, how to identify a deformation in terms of the fluid flow field has already been discussed, but today we will start with properties of the stress tensor. Body forces, where a force is acting on each atom or molecule, or each the entire mass of the fluid elements, are easy. But we shall be discussing viscous stresses. Thereafter, we will write down the viscous stresses in terms of the uh, in terms of the strain rates, and we have faced the strain rates and those terms even previously. And finally, we will write down the so-called Navier Stokes equation and the fluid dynamics equation. Uh, yeah, so that's how it goes. So fluid dynamics, so we were discussing kinematics till now, and well, Euler equation was also a fluid dynamic equation, but where we neglected the viscous terms, and the viscous terms will be the primary uh, points of discussion today, and that will, as you'll see, will complicate matters. So fluid dynamics is basically a discussion about forces acting on a fluid element and the strain rates produced by them. Forces produce strains, and forces are written also in terms of strain rates, in terms of proportionality constants, as we shall see. uh, Okay, so that's the initial background. Just to get started, suppose we will discuss about a fluid at rest. Suppose there's a fluid element, and it has been divided into two parts. Fluid element uh, 2, and this is fluid element 1. And basically, fluid 1 gives hydrostatic pressure. So this is fluid at rest. Hydrostatic pressure to fluid 2, right? So the pressure which is acted upon by fluid element 1 on 2 acts in this direction. If we take this to be the surface normal is in this direction. And similarly, fluid element 2 gives hydrostatic pressure um, to fluid element 1, right? And the stress acting is force by this area element dA, and it is isotropic and independent of orientation of dA. So if fluid is at rest in all directions around a small point, the pressure acting is isotropic and independent of orientation, right? So that's what's fluid at rest. Now, slightly complicating the matter, if fluid is in motion, there will be additional tangential forces. So if this is the surface element, the hydrostatic pressure was acting normal to the surface element. But if a fluid is in motion, you can have additional tangential forces acting. So if this is the surface, there could be forces acting on this direction, whereas the normal is the normal to the surface, right? So, and that could act between layers of um, fluid having relative velocity with respect to each other. the point is having relative velocity with respect to each other. Del Vx, del Vy. So that has relative velocity between layers of fluid, right? And these forces are, as origin is viscous forces. And what do viscous forces do? Viscous forces transport momentum from a region where there is high momentum density to a region of low momentum density. And as we discussed in one of the previous classes, the kinematic viscosity, which is eta, eta is the normal viscosity by rho. Viscosity by rho is the kinematic viscosity, that is the diffusion constant of momentum transport, right? In addition, you can have also momentum transport where amount of fluid of high momentum actually transports en mass. It reaches, that entire fluid element reaches from this point to that point. So you also have momentum transport due to that, and that is typically taken by the v dot grad operating on v. But here, in additional, the viscous forces lead to you have additional viscous forces which act tangential uh, between layers of fluid having relative velocity to each other. Okay, now we are talking about viscous forces, tangential forces, normal forces, and in general, uh, force acting per unit area. uh, I mean, suppose you fix a coordinate system, and then for simplification, you could have dAx, dAy, and dAz. This should be Z. So normal to different areas. Let's take a cubic box, and through each area, through dAx, you could have x component of momentum which is acting on the other fluid element. You could have y component of momentum which is being transported and acting on momentum being transported, force acting, and you could have the z component. So in general, it will be a 9-component tensor. So in general, the viscous forces will, or the viscous, it will be a viscous tensor, shear stress tensor, right? Uh, so so now we will simplify things a bit. For simple Newtonian fluids, where molecules are not rod-like or chiral, and there are no magnetic particles inside the fluid, and which could lead to additional complications. And if one has forces which are conservative, and suppose there are no density gradients, we are not at the moment considering density gradients due to grad T or grad P, right? Then in that case, uh, the viscous forces uh, which are generated, are related uh, to the symmetric part of the velocity gradient tensor. So in general, if you have del Vi, del Vj, del Vx, del Vy, if you like, rate of change of Vx in the y direction, that in general can be written as a symmetric part and an antisymmetric part. So this antisymmetric part is related to the rotation of a fluid without deformation, and that does not create viscous stresses. So today's discussion will be about this part, the stresses and the forces and whatever which the symmetric part of the velocity gradient tensor, what forces are created, are generated, are felt uh, due to velocity gradients. On the other hand, you could also say that yes, there are velocity gradients, hence there are forces which further deform the flow, and vice versa. So they act on each other. A matter of convention, I'll be mostly following the physical hydrodynamics by 4 authors, but sometimes there are some parts which are better explained in the Kundu book. So, however, the problem is these two books have a different different convention. Have a different convention, and if you had, suppose this was a fluid element of, and this was J vector, this is normal to the surface, then in the physical hydrodynamics, sigma ij, the stress tensor, the components of the force, is defined as sigma ij, where the force is acting in the I direction. Force in the I direction is acting on surface AJ. So the force I is written first in physical hydrodynamics, and the surface normal J is written second. And yeah, so for simple cases, it actually doesn't matter, and the reason you will know in some time. Whereas in Kundu, it first, when sigma ij is written, it says on surface AI, force J acts. Okay, so the definition of this stress tensor is different in the two books, but it really doesn't change the mathematics much. I'm just telling you, so this is something which you might spend some time unnecessarily getting confused about. So sigma ij, is the stress tensor, can be written on as sigma xx, sigma xy, sigma xz, and as per physical hydrodynamics, you have the x force in the x direction acting on surface area, on a surface element whose normal is in the x direction, whose normal is in the y direction, and normal is in the z direction, right? And similarly here you have force acting in the y direction on a surface element whose normal is in the x direction, whose normal is in the y direction, and whose normal is in the z direction, right? Now typically, as we'll see, that's sigma ij is equal to sigma ji. So sigma xy will be equal to sigma yx. Um, for for simple cases, as long as the molecules are not rod-like chiral, there are no magnetic fields, and the fluid objects are not, molecules are not magnetic, and so on and so forth. So this will generally hold true, and that will come from that viscous forces only deform and do not lead to solid body rotation of a fluid element. So this condition will come from that, as we will see soon. So the point is that viscous forces do not provide torque. Even if there is del v x del y, it can be broken up into the only symmetric part of the velocity gradient tensor, which provides deformation without rotating it, and the antisymmetric part, which rotates the entire fluid element as a block without forming deformation. And why is that so? It was actually derived in one of the previous classes. And so if you take this to be the fluid element, I'm simplifying this derivation a bit. It can be done more rigorously, but I want you to have the physical ideas. Now suppose this is the x direction, and you have Fy pointing in this direction. So sigma yx, as per physical hydrodynamics convention, is F force in the y direction acting on an surface area element whose normal is in the x direction, right? Now Now, suppose this was a very small element of fluid uh, whose center of mass is not moving, and this is important because we'll see why. Uh, because never mind. So here in the, so if there's an element of the fluid, this this fluid is acting, is giving a force to this fluid, and the force that this fluid is giving to the other, just the other, is basically uh, in the opposite direction. Hence, this green arrow is in this direction, this green arrow is in this direction. The point is, this force is equal and balanced. It's a very small element of the fluid, and this force which is acting, it's not changing the center of mass of the fluid. There is no or not changing the density or the center of mass of the fluid. If these were different, then there would be a net flow of the fluid. These are equal, uh, and they will be related only to the velocity gradient tensor. Yeah, velocity gradient terms. And that means these forces are acting only to deform the fluid element, local deformation of the fluid element, no rotation, no center of mass motion. If there was an unbalanced force, then the entire fluid would move. Okay, so we are looking at only deformation forces. Maybe you'll have to listen to this twice to get the point, but so here we are looking at only parts which are do shear, which deform. So those forces, these are equal and opposite. And similarly, in suppose this was the y direction, so this is the day, and suppose there was some x force, force in the x direction acting on an element day. Day is normal to the force, and the value of that area element would be dx, right? Dx and into dz. Suppose this is the z direction, this is the y direction, so this is dy, if you like. This is dy, this is dx, this is dz. Then the total torque acting on this fluid element in the z direction, say, uh, in the z direction, will be the force acting in the y direction, so it's sigma yx, which is force per unit area, into dy, dz is the force, and the total torque acting, it would be the distance between these two forces, dx, right? uh, so this is acting in this direction, this is acting in this direction, but there's a torque which will depend on the distance between. To take this dx dy dz equal to 0, and similarly the torque acting on this is sigma xy into day, which is dz into dx. That's what I've written, dx into dz. And the distance between the two torques acting, one is in this direction, the other is in this direction, both have magnitude sigma xy. Since viscous forces don't rotate, do not result in a net rotation of the fluid, so this torque has to be 0. And as a consequence, sigma yx has to be equal to sigma xy. That's exactly what we said here, and that is the reason that this convention doesn't finally matter for simple fluids only. Okay. Uh, so in some books, they write that they are equal because of the equilibrium equilibration of torques, equilibrium between torques, and so on and so forth. What I understand from there, from all these various terms which they use to justify that basically viscous forces will result in no net rotation as a rigid body, as a consequence of which ax by ay and Fy by ax have to be equal to 0. If the torques are not balanced, then there would be rigid body rotation, and that is not related. So viscous stresses will be related to the velocity gradient tensors, as you will see. They are not related to this part of the velocity gradients. This part, I want to remind you, is the part which leads to deformation of the fluid. It leads to deformation, distortion of the fluid. And yeah, so it can be also, I don't know what, I think I missed out. Oh, this is del vi del xj. So this looks a bit like x, but this is del vi del xj. So that's how you can essentially write it. And this was, yeah, the symmetric part of the tensor. And suppose you had so suppose you wanted to calculate the force, say, acting on the x direction, you would not only have to take sigma xx, but you also have to take the force, this viscous force, which is acting on this surface in the x direction, on this surface in the x direction, and so on and so forth. Right? So that will decide the total force acting in the ith direction. Right? Especially if they're unbalanced. But at the moment we have balanced forces. So basically, yeah. So if you want to calculate the forces acting in this direction, that's how you do it. Okay. So the next thing we are going to do is so this sigma ij, the stress tensor that we have been talking about, has also a part which is coming from the thermodynamic pressure. So basically, viscous forces act only when there is fluid in motion and there is relative motion between the layers of the fluid. If the entire fluid is moving as a bulk, just, I mean, it's like moving without any relative motion, then you are not going to see sigma dash ij. So sigma ij is being broken down into two parts, which on a part which appears uh, only when there is relative motion, which causes strain rate. It's called the viscosity stress tensor. And for incompressible fluids, and only incompressible fluids, it contains doesn't contain any diagonal term and causes deformation of the fluid element. Deformation, it can cause volume deformation, which is called dilatation, or it can call also shear, which is called the deviatric part. So it does not cause net flow or rotation. On the other hand, uh, you can also have a pressure term, and this is isotropic. It also acts for a fluid at rest or uniform translation. I already mentioned it's isotropic and also acts in absence of velocity gradients. And the reason this comes with a minus sign is that the pressure on a fluid element acting by the rest of the fluid acts inwards, and which is opposite to the normal, which points outwards. So hence it has been broken. So this sigma, the stress tensor, has been broken up into these two parts: the viscosity stress tensor and the pressure component, the thermodynamic pressure. Later we'll have also something else, but we'll wait for it. Okay, so till now we were just talking that, well, viscous stresses and stress can be defined which act on a surface. So if you have a fluid element other than the body forces, you can also have forces which act on the surface of a fluid element, and both this and this act on the surface of a fluid element, but this acts even when a fluid is in motion or static, and this acts only when a uh, fluid is in motion. Now here I want to pause a bit, uh, being a bit finicky, but these details and discussions are important. Now, this concept of pressure, especially thermodynamic pressure, equilibrium pressure, statistical physics pressure, is defined only, when a system is in equilibrium, when there is no flow, when there is no current, especially if you have taken the statistical physics course or even the computational physics course, when there is no current. But here we are defining the equilibrium or the thermodynamic pressure. And that is possible because, remember, right in the first class, I said that your fluid element is large enough and the time of motion we are looking is large enough, within which there have been many individual molecules which have undergone collisions with each other and come something close to a local equilibrium. You cannot use these equations when the time of motion, when the rate of change of the fluid motion is either too small, so that there are not enough particles which undergo collisions and reach equilibrium, nor can you look it up at times where equilibrium due to many molecular collisions has not been reached. So you are considering, even if the fluid is in motion, that each element of the fluid is in a condition of local thermodynamic equilibrium. And you are talking about pressure. That pressure is what you are talking about, that hydrostatic pressure, if you like. Now, again, uh, the relation between the stress tensor, yeah, the stress tensor and um, the velocity gradient element. The velocity gradient itself is a two-dimensional tensor. This is a tensor, and basically the coefficient relating the two is a fourth order tensor, but then it can be shown uh, by some tensor algebra that not all the components are independent. So what I have spared you is the trouble of doing some tensor algebra, and I am finally taking the consequences so that we can more focus on the physical picture, on the concepts rather than the algebra. Okay, so basically what I have written here is this stress tensor with a dash. This is the total sigma ij, is the without the dash, which also incorporates the pressure terms, and this dash is the part which is the viscosity stress tensor, which acts only when the fluid is in motion, with the dash. That can be written in terms of the bulk viscosity, which is related to dilatation. Dilatation, divergence V, uh, not equal to zero. So and there's an entire volume change. So if there's a volume change, that was dilatation. It can be written um, in terms of that, where you call it, this is the bulk viscosity related to dilatation, and the term vanishes as divergence V equal to zero if there is nearly incompressible flow, and the normal viscosity, which depends. So this is basically the diagonal paths, and this is the dynamic viscosity. this is called also the dynamic viscosity, which you relate to the viscosity. And remember, eta by rho is the kinematic viscosity, right? That's the diffusion constant for momentum propagation. And so this can be written in terms of eta into 2 times Eij minus 1/3 delta Ij ELL. Remember, there's a double. This essentially means that it's the same as this divergence V. So why does this come? Why are we writing like that? We'll come slowly to it. But let's look for the simplicity of incompressible fluids, so that divergence V equal to 0, then you immediately know that sigma dash ij is equal to 2 eta, 2 times viscosity Eij. So you have this two factor here, because you basically want to say that the stress tensor, the viscous stress tensor, depends on viscosity terms del Vx del Vy plus del Vy del X. Okay, remember this Eij term, when we decompose the symmetric part, it comes with a half term, and this 2 is here essentially to take care of that. So what you have is that if del Vy del X was equal to 0, the stress acting between two layers of the fluid is viscosity into del Vx del Y. Now that is something which you have seen. So sigma dash Ij equal to viscosity. It's also called the ordinary viscosity or the shear viscosity. First coefficient of viscosity, different books have slightly different term, but typically we relate it as the shear viscosity. And that, so when written in terms of Eij, you have an extra 2 factor, but in general, since you have 2 and there's a half that cancels, and you have del Vi del Xj plus del Vj del Xi. When you write I equal to, when you write this as xy, you have eta del Vx del Y plus in general del Vy del X. But if you had that pure flow like that, what the deformation part, the shear stress will do, that it will be proportional to eta into del Vx del Y. Right? Now, this quantity, eta, for complicated cases like when you have pneumatics and so on, flow in different directions. If you have rod-like molecules, the entire the fluid is made up of rod-like molecules pointing in the same direction. Then, if in the direction of the axis of the rod, the flow properties will be different. The direction perpendicular to the axis of the rods, the flow properties will be different. But if you don't consider such cases, when you have simple cases, when you have a simple Newtonian fluid, for that viscosity is the same and is independent on which plane you take it. So it does not depend whether this proportionality factor does not depend upon whether you're taking it del X, del Vx, del Z or not. So it's basically isotropic in all directions for normal Newtonian fluids. Okay. Now, yes. Now, think they miss something. Yeah. So, so this equation is copied in the uh, in the in the slide here. So here the point is, you also have this term. You also have this term, and you have an eta sitting in front of it. Okay, so first of all, let's have a look of how this term is going to look, right? So here what it is saying is, so eta 2 times eij minus 1/3 delta ijell, right? Now for normal simple fluids, this will be equal to 0. I mean, the diagonal terms will be equal to 0, so that only the off diagonal terms act. And the way this has been written is del vx, eta, I mean, there's this 2 eta term, of course, this 2 eta term, but then this is del vx minus 1/3 this ell, if you remember. Um, so what would be ell? So I and I will be the same. So what you will have, so where is where is the general expression for, yeah, eij, right? So this will be exx. So half del vx del x plus del vx del x. So this will be eij, will be, I mean, in terms of xx, it would mean simply you would get a factor of 2 from here and a half from here. So it will be del vx del x. But remember, when you're writing this in the tensor notation, it means that you are summing up all the terms, right? So hence you have 1/3 into del Vx, I mean, basically divergence of V, right? And and uh, in general, in general, uh, even if divergence of V was not equal to 0, even if divergence of V was not equal to 0, uh, so then this del Vx will be, except in rare cases, for simple fluids, compressible fluids, um, the 1/3, the average of this will be equal to del Vx del x, and this will go to 0. Similarly here, and then similarly here. But then why have we written it like this? Why complicate matters like this? Right? The reason it is written is when you have complex fluids made up of polymers, fluid made up of liquid crystals, then you can have that even if you calculate this as a mean, the different diagonal terms can be different. And then you will have something called the normal stresses. So that is the reason it is, and it is related again to viscosity, the same dynamic viscosity. Okay, and that is different. And that is different from the bulk viscosity terms. So in general, this is written in such a manner so that for simple fluids, the diagonal term becomes equal to 0. But writing it like this also accounts for the fact that you could have cases where these terms have different values, which will lead to the creation of normal stresses, about which I'm not going right now. But if the diagonal terms happen to be 0, as will be the case for simple fluids, because you have 3 terms here, and that will be equal to this, so it will cancel off. So this will be, yeah, so in general this will be 0 for simple Newtonian fluids, and then you will have essentially only these terms, del Vx del y, del Vy del x, and eta by 2, because this is eta ij. It has a half factor. And just to remind you, I have put it in different colors, right? So this is del Vy, del z, del Vz, del y. And since stress tensor is being written in terms of eta into this Eij, you automatically know that this is equal to this, and hence sigma, suppose this was yz, is equal to sigma zy. Similarly, sigma xy equal to sigma yx. Here I didn't have space to write sigma xz and sigma zx, right? But you can guess what the terms will be. I think I should drop this eta. The viscosity term is even here, right? So in all of this, the viscosity should be not here. You should have the factor of half, but not eta, because that is sitting outside. This is just the pure deformation. Basically, you're writing down the pure deformation tensor here, right? And how would this look? This again would be, well, so exx would be mm, del Vx del x into del Vx del x into half. So it would basically be del Vx del x, if you like. And this entire tensor, remember, there's a summation by Einstein's convention, and then you would have identical terms setting here, right? So that would be typically the terms which would be sitting here, right? And this is written in terms of the most general form, where one had broken up the the dilatation part and the deviatrix part. So this is the deviatoric stress tensor, if you like. So it's a bit intricate, but yeah. Uh, so that's what I wanted to write here. Yes. So the other thing which is there to note is, when you look at this, the stress acts. Uh, so basically, what is happening is the average deformation that one is going on. If there is extra deformation beyond the average, right? That's what contributes to the stress. It's not about just pure dilatation. So suppose there's some amount of deformation which is happening, and it's different in different directions. So the deformation about the mean is what is contributing to the shear stress. And note, this is del Vx del x, right? And it comes with this dynamic viscosity. So that's the other thing to note here. Um, and this is explained well in page 97 of Kundu. Of course, the problem is they have a different symbol for bulk viscosity and a different symbol for the dynamic viscosity. But anyway, it is explained well in page 97 of Kundu. So that's what I wanted to say. So what I have done here is taken the previous equation, and if you just take the shear component, and if in general sigma xx, so I'm focusing only on the diagonal components, need not be equal to the sigma dash yy, need not be equal to the sigma dash zz, especially for complex Newtonian fluids. This will be true only for complex Newtonian fluids. And then you can define something called the mean mechanical pressure as different from the thermodynamic pressure, right? And that will, this mean mechanical pressure um, is basically these terms into 1/3. Okay. And if you are writing in terms of stress, then of course you have the 2 eta also. uh, but the diagonal terms can also contribute to the stress. This is different from the bulk viscosity term, which was more isotropic, right? So we have included all the parts of the various kinds of deformations that can happen, and this deformation can, yeah. So when you write it in terms of in a particular direction, so it's 2 eta del Vx del x minus 2/3 eta divergence of V, which is being written, and here we are focusing only on the diagonal terms. Similarly, sigma dash yy will be 2 eta del Vy del y minus 2/3 eta divergence of V. And yeah, so here I already explained how how this term is going to look. This eta is to be this eta is already here. This should only have the velocity gradient terms. Yeah, so I made this mistake. And I already started with this, but as Kundu states, there can be body forces, something like gravity, which acts on the density. It's like the entire mass of the fluid is acted upon by the gravity rho dv into g. And one can have conservative forces or non-conservative forces, body forces. One can have surface forces, and that's what we have been discussing till now. And there can also be line forces, and these typically are stated in the problem through boundary conditions, right? And again, uh, again, suppose one had a fluid element of this shape. One had a fluid element of this shape where these 3 planes were really parallel to the xy, the xz, and the yz planes. But there was another fluid element. This completed the triangle along this red line. The normal, suppose, was in this direction, and suppose that the force acting on this surface, on the surface forces, was in this direction. Then one can write the stress acting, the stress acting on this surface is df ds, and that in turn can be written as the x component of the force acting on the, so basically this is what you have to do: sigma xx into nx, sigma xy into ny, where you have broken down this n component into x, y, and z, right? And this is the force acting. This is the force acting on the x surface in the x direction, the x component of force acting in the y direction, the y surface. Surface is normal, is perpendicular to the y, right? So basically that's the force acting on this surface. Now we have just, so in the x, the y, and the z. So that's how you write it in terms of, note that this is written in terms of the stress tensor. With this background, let's actually come to the equation of motion. So now we are really writing down the momentum conservation for equation, because now we know how to write the forces, the surface forces. So body forces was trivial. M d2r dt2 was discussed right at the first part, where you had the Euler frame and the Lagrangian frame and so on and so forth, right? So I mean, you could look at a certain volume of fluid, and you could keep looking at the same volume element of the fluid, which is unchanging function of time, or you could look at a particular element as it is flowing around with the fluid. So its density can change as a function of time. Moreover, the volume element itself can change and deform and flow around, carried by the fluid. But the total number of elements within the fluid elements remains the constant. And to account for that, we have written ddt. This is ddt. Del t would be when you are just looking at a certain element here. What is happening is a certain element of fluid is flowing in the flow, it's deforming, it's changing, but the number of molecules within the fluid element remains unchanged. And Euler from the bridge is seeing this fluid element flow along the fluid, and hence you have a ddt of rho f, fluid density, into velocity into dv. So basically this is the momentum density of a fluid element as it flows along, and that is equal to, so this is, if you like, m d2 m d2 sorry, m dp dt, so which is the Newton's equation. That is equal to the all the body forces, gravity or whatever could be acting electrostatic if they were charged, plus the surface forces. So this element of fluid is also going to deform as it flows around. Okay, so it's flowing, its center of mass is moving, and also it is deforming locally. If you were sitting in the center of mass of that flowing as Lagrange would, then the shape would change because of these surface forces. In addition, they would flow, right? So 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 this is, so basically you are looking at the sum of forces acting on its different areas, right? And that would, so that would also, so this in turn can be written as del x of sigma ij, using the Gauss's theorem again. Now note, del xj sigma ij essentially means that there is a space dependent of sigma ij. Sigma ij, so you're looking at a fluid element where these stress forces has a functional dependent on space, on x, y, and z, right? So basically then, and suppose density, well, yeah. So I've taken the rho out of time, assuming that, I guess, it's not changing as a function of time in compressible fluid. So if you take that, if flow is unchanged and dv dt, and remember dv dt can be written as v dot grad acting on v, right, plus explicit time dependence equal to rho f into body force and divergence of sigma, where sigma is a tensor, and divergence of sigma, however, is in a vector. So divergence of sigma in the ith component, basically you have del x acting on the first element of the row of the tensor, first element in the first row, then you have del y acting on the second element of the first row, and del z acting on the third element of the first row. And of course, if you don't have a second or third element, then of course that's a different case. And this is the general shear stress tensor, which will have this dash term, is the viscous stress tensor, minus grad p, which will sit only in the diagonal terms. So which in turn can be written as divergence of sigma dash minus del p del x I, because you have taken the ith component in general, right? So the Navier Stokes equation, when if you're looking at a fixed point in space, rho f del v del t, right? The velocity change locally. Density has not been changing. We are into v dot grad v, and that is called the advection term. These are the body forces minus grad p and divergence of sigma dash. So, which will have the tangential forces, compressible forces uh, in in plus the normal stress. We could have also diagonal terms, right? Even in the dynamic viscosity term. For non-moving fluid, this on the left hand side of the equation will be 0. Also, this term will be 0 because this relies on the relative motion of the fluid, and so you will have rho f grad f minus grad p equal to 0, right? So that's what you will have for a non-moving fluid. But if you have a moving fluid, then basically I want to explicitly calculate this term. So what I have done is take, I mean, take this term and act and make the divergence act on it. So this is written in black. So basically what I've taken del x of this, right? Because it's in the diagonal term. In addition, you have to take del x of this, del y of this term, right? Because you're taking divergence. So basically here you will see, so the theta won't be here, but you will have del x of these terms, del x of all these terms, del y of these terms, del z of this term. In addition, because this is also in the diagonal for the total, if you don't break it up into the dilatation and the deviatrix part, right? The isotropic part has been taken apart from using minus p, but the other parts remain. So you have divergence of this term as well, and let's see. So this is the bulk viscosity del x of this term. Okay, 2 eta del x this term, and note there is no half here. Here there is a half, here there is half, here of diagonal terms had half, but here there was no half. The theta shouldn't be there, right? But 2 eta is here outside. So you don't have a half here. So you have taken the del x of that diagonal term as well. Then del y of the two terms of sigma xy, and del z 2 eta del z of sigma xz. And of course, that can be written as 2 eta into del vy del x plus del vx del y, and this is del vz del x and del vx del z. The reason I have written it in different colors is that this term, when del z acts on this is essentially like a Laplacian of vx. Del y of, I mean, double derivative with respect to y of vx. That sits here. And similarly, del x into del v del x, it sits here. Now note that here there was a 2 eta and there was a half here. So you had one contribution from here and here, but here there was no half. So I have written here no half factor here, right? So there was 2. So one of the del vx del x acting on it actually comes and sits here. So this is basically Laplacian of Vx. We are writing down component wise. So what we are trying to do is divergence of sigma dash, the double lines is because it's a tensor. It's just writing down the x component, divergence in the x, yeah. So we're just writing down the vector sign in the x direction, taking the x component of this, and so this is sitting here, this, and one term from here sits here. And remember, you have another eta del Lx acting on del x, del Vx del x is sitting here, right? Uh, yes, and that, and there is also del Vx del x sitting here. That actually, yes. So this 2 will go inside here. This 2 will go inside. Remember, here there were 2 terms, one of which came here. The other term, because there was 2 here, remains here. This 2 goes here. So del Vx del x minus 2/3 del Vx del x is 1/3 del x of del Vx del x. And similarly, there will be 2 other terms, and they will contribute here, del Vy, del y, del Vz, del z. So basically things will come here. As a consequence, this now, if you simplify, can be written as eta grad square V, which is essentially this term. You can write, if you're looking at only the x component, then you will have a Vx here. This is a vector equation. And then the bulk viscosity and eta by 3, the bulk viscosity and eta by 3, I missed eta here, I think. Yes, this eta has been missed here. So we'll have an eta. So this essentially, those 2 terms essentially comprise of this, because in both you have del Vx del x, del Vy del y, del Vz del z. Both you have, but this comes with eta and this comes with zeta. So this is bulk and this is dynamic viscosity. So basically here I have further broken it down and written in the x component and the y component. And if you have done that, then you know essentially how to write down this expression. So this is a vector equation, and this is the Navier Stokes equation. This is the most general equation for Newtonian fluid, where I have kept extra terms. Things can be simplified even further, so you won't have off diagonal terms. Often divergence V equal to 0, but those we're going to discuss in the next module.